Hello, this is Schweitzer, and I'm going to do a couple quick small video here. Only going to do a couple things here, but one of them is going to identify, you should be able to identify a strong acid from a weak acid. Straight up. Number 2, calculate the pH of a strong acid. And number 3, calculate the pH of a weak acid. So first off here, how do I identify a strong acid? Well, there are 6 strong acids. These are the 6 strong acids. If you come across an acid and this is not one of them, like if you come across, let's say, HF. HF is not on this list. It is an acid, aqueous here, but it's not on this list, so therefore it is going to be weak. Okay. So the first thing, you have to write these down and know these 6: hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, and perchloric. All right. So how do I determine the pH of, or calculate the pH of a strong acid? Well, the fact that it's strong means this thing goes entirely to products, meaning that this reaction will go to completion. Okay. Now, ultimately, to determine the pH, I need to know the ending H3O plus solution. I need to know this concentration right here. Get rid of that for a moment. And now, here we go. I need to know this concentration in the end. Okay? Once I have that, I'll take the negative log of the H3O plus concentration, H plus, and this will equal the pH. Okay? Because it goes to completion, it's pretty much 1-to-1 ratio. I'll lose 0.5 of this. I'll have 0. Again, this is going to completion. This will not play a role because it doesn't have a concentration. I will lose some of it, but it should be there in a liquid state. I can't increase or decrease the concentration of the water. It's water. I will gain 0.5 molar of this, and I will gain 0.5 molar of this. This will be down to 0.5 molar, and this will be 0.5 molar. Again, I have this here, but this is not contributing to the pH. This is the pH right here. Negative log of 0.5 molar. Okay. Now, let's just say hypothetically you don't have a calculator on you. You should note that if you have a 1 molar solution, it would have a pH that is 0. The negative log of 1 is 0. 0.1 molar solution would have a pH that is 1. So we're in the middle, and it's not going to be exactly, because it's an exponential scale, but we're somewhere between 0 and 1. So if I take my calculator and type in the negative log of 0.5, and you get 0.3. And so this is going to be equal to a pH of 0.3. Obviously very acidic. Now, what about a weak acid? Okay, I'm going to flip over to a different page here and calculate the pH of a weak acid. All right. Now, fundamentally, a weak acid, okay, let's try HF, for example, okay, it will also undergo hydrolysis, which is going to be plus H2O going to H3O plus and F negative. Okay, this is the forward reaction. Theoretically, not theoretically, in reality, there is a reverse reaction that's kicking backwards, that's fighting back. If there was no reverse reaction, this would just go to completion. But there is a reverse reaction, and that reverse reaction is represented by this arrow right here, and I will draw it out right here. Now, in this case, I'm going to put it up here. The F negative will react with water to produce HF, this stuff right here, and hydroxide. It is the reverse reaction. We can deal with either one of these reactions. They both have a reverse. We don't have to deal with both of them at once. We'll do one or the other. This technically has the reverse built in by adding this arrow. This has the reverse arrow added in by adding both arrows. We do with one or we do with the other. Okay. Now, initial concentration is 0.5 molar. Okay? The result of this reverse reaction is that I won't be going to completion. So fundamentally, the difference between completion and equilibrium is that I don't run one of my elements down to 0. Initial, Stoichkov ratio, ending point. Now, I don't have any of this to begin with, so I will be tracking my concentrations. Again, this guy doesn't have a concentration to track, but at equilibrium, I will be filling it into my equilibrium expression. Equilibrium expression is K equals these two concentrations, the F negative divided by HF. Okay. Each of these values here is represented in this equation and given as a K. Ka, because it happens to be the acid equation. This is a constant at 25 degrees Celsius. This is going to tell us to what extent the forward reaction can compete against the reverse reaction. The reverse reaction at this point doesn't have any initial concentration of fluoride, so it's 0 and 0. So at this point, this reaction starts shifting towards products, okay, and produces some fluoride, some HF plus ions, and I lose some of this. All right, so how does this work? I'm just going to run through the mathematics of this. One, I need my Ka. So you go to a chart, or it would be given to, and what we got here, it should be here somewhere. If you don't have it, you can always look it up. And science resources, it would be on equilibrium constants, and there it is. I must have deleted it. So go down here, and you'll see HF. All right, there it is. And I even have the hydrolysis equation here. This is the acid hydrolysis equation. And the Ka is 6.6 e to the negative fourth. Okay. Now, 6.6 e to the negative fourth, without complicating things too much. You go minus x, plus x, and plus x. Now, I can't put a minus 0.5 here because I don't know that I lose all of it. In fact, I would say, based on this K, that I am really, as far as a weak acid is concerned, reactants going to products, okay, that the majority of my materials are staying on the reactant side. I don't get many products. Look, this fraction has to equal this. Okay, this is going to be 0.5 minus x. I'm going to flip back to my black. This will then be x and x. Let's plug these values in. 6.6 e to the negative fourth equals x. I'm going to plug this into here, and this into here. So x times x over and 0.5 minus x. Okay. Now, as I plug mathematically to solve for x, this would be x squared. Putting this over here, we would end up getting a quadratic equation. We will use our shortcut rule here, which hopefully has been explained, but I'm going to essentially remove the x off of here. Okay. And multiply by 0.5, and then square root both sides. 6.6 e to the negative fourth times 0.5 equals x squared. So I will then square root both sides, and this is my value, x equals. Grab my calculator here. I have 0.5 times 6.6 exponential to the negative fourth equals, I got 0.00033. I will attempt to square root that guy. And I get 0.0181. 0.0181. That is x, all right? That means of the 0.5, I've only lost minus 0.0181. Therefore, I could then subtract that from 0.5 to get my concentration that's left. And I got 0.0181 here and 0.0181 here. To get the pH of this thing, I simply take my concentration of my H plus ions that I got, okay, and plug it into my equation. Negative log of the concentration of 0.0181 equals, all right, negative log of that answer is 1.74 is my pH. Okay. Notice that we don't get nearly the pH we got on the other strong acid. We didn't get nearly the amount to kick over. So in this case, the strong acid wasn't really effective at kicking over to the product side. Only of the 0.5, we only got a small amount. If I wanted to get more acid, I have to crank my concentration up. That would cause this bottom character to be larger, and therefore I need more of this to balance off it in order to maintain this K. Or fundamentally, you need an acid with a larger K. Larger K means the forward reaction is more prevalent. So either of those options would give us more H plus ions in the end, and therefore a more acidic solution. Just one example. Okay, terms: concentrated strong, concentrated weak, dilute strong, dilute weak. Okay, so let's draw some pictures of these guys. I have, my first one I'm going to do is a concentrated strong acid. Okay, there are two terms here. One is involving concentrate. This is really referring to moles per liter, and strength of the acid means if we have an acid, what fraction of them kick over to products at any one point in time. Does it go to completion, or does we only get a little bit at a time? So if I take a beaker and I would draw, let's say, an acid, okay, let's go with, pick a strong acid, H. I'm going to go HX, a standard acid. It's a strong acid, so there's 6 options I could have chose for this acid. But as soon as it gets dissolved in here, every one of these guys will undergo hydrolysis. H2O goes to H3O plus X negative. So in this situation, we get H plus ions. Now when I write H plus, this means H3O plus, and it's just the way it's written. It means this, and I don't have a lot of room here, so I'm just going to H plus ions. And every time I have an H plus ion written, I have to write an X negative floating around as well. The fact that it is a concentrated acid means that I have lots of them in here. H plus, X negative, H plus, X negative, H plus, X negative, H plus, X negative, okay? I would expect this thing to have a very low pH, meaning it's very acidic, okay? That's it. I guess that's all I would really expect. So let's look at another option here, a dilute strong acid, okay? All right, so again, we'll draw ourselves a picture out here. Okay, and I'm going to drop in here the same HX. It's still going to be strong, so every single one of these guys is going to break into its constituent hydrolyzed ion and cation and anion. So H plus, X negative, H plus, X negative, H plus, X negative. Now in this case, again, I don't have that many H pluses here. But usually speaking, I still have a relatively low pH, okay? Because even a dilute acid, strong acid, is going to be able to produce a decent amount of these H plus ions. It would just be dilute, okay? Let's roll down a little bit here, and let's consider the fact of a concentrated, okay, concentrated weak acid, and we'll also consider a dilute weak acid. Okay. Now, let's draw out 2 more pictures here, and then we'll be done. A weak acid inherently, HX plus H2O yields H3O plus and X negative. Inherently, this forward reaction is just very small, okay? And therefore, we will have, on the factor, depending on the acid, we could have let's just say HF, which was here earlier, we had this guy, which means that basically every 10,000 of these HFs, only one of them kicks over, okay? Another way we use to express this is percent ionization, and we'll maybe cover just one quick example of that towards the end here. But in this case, yeah, it could be as much as 1% flipped over, or even less. That could be 0.01% or 0.0001%. It could be 1 in every million flip over. Very often, we don't have very many of them flipping over. So let's draw a picture out here, and we have ourselves a beaker, and as soon as I drop this HX in here, it starts to ionize, but very small amount. Most of them stay as HX. Okay, HX, 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 and it's concentrated, so we have a lot of them. Now, I would have a hard time drawing proportionally the number of these that would be here for every one of them that might flip over to an X negative and an H plus. And I could probably keep drawing as many of these in here as I can, and that would be getting closer and closer to the right proportion between this. Okay. In this case, we would expect this thing to be a pH range of somewhere between 2 and 6, because I just don't have many H pluses around. A dilute weak acid, okay, similar situation here. I have HX, okay, and it will also undergo hydrolysis just like this one will. As I drop in my beaker, I draw my beaker first. Ooh, got a little bulge in it. All right, got some water there, drop some HX in there. Again, I do have some of them, okay, HX, 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 and in this case, again, the drawing wouldn't be real proportional, but I'd only have, let's just say, one of them, okay? And to make my drawing a little bit better, I'm going to draw another one here, just so I have a few more over here versus over here, okay? So again, a pH in the range between, probably 4 and 6. It's still acidic because I still have acids in here. Just not very many of them, okay? So percent ionization is something that is inherently, you can see in these pictures here. This one here, I'm going to put this right inside of this box right here, would be percent ionization. That would mean, based on the amount I have, how many ionized, and therefore, for a strong acid, this would literally be 100% ionization. Okay, that's the definition of a strong acid, even here. But what about a weak acid? You would need to say, okay, well, how many of these things actually ionize compared to how many were in there before? So the calculation for this is going to be the original concentration. I'll put ORG, and then the amount that actually flipped over, or the amount that actually changed. I'm going to put X on here, and then times 100. And then I'm going to do this calculation on the other side. Question mark here. Okay, right here for, it doesn't pay to do a strong acid. A strong acid would simply be Well, it'd be the percent ionization of this guy would be, well, my original concentration was 0.5, and how much changed over? That's the stoichiometric shift. Well, 0.5 of them shift over. Okay, well then times 100 equals, 1 divided 0.5 is 1. 100% ionized. Okay, that's the case for all strong acids. Flipping here, we have a weak acid. Okay, now in this case, I have my original is 0.5. So of my 0.5, how many actually flipped over? Only 0.0181 times 100. And this is going to give me my percentage. That's going to be 0.5. Turn my calculator on. 0.5. 0.0181 divided by 0.5 says 3.6% actually ionized. And that's pretty common for a weak acid, very small percentage, as opposed to 100, okay? Strong concentrated, strong dilute, weak concentrated, weak dilute. All interesting stuff involving acids, okay? Thank you very much.